Okay, so we want to, in lesson number 5, we want to actually go over a little bit of the special relativity because as you'll remember, we started special relativity at the very beginning of our course. And now we're going to come back to it. Now that we've done a little bit more physics, we can have a little bit more fun with special relativity. What we looked at earlier was a couple of Einstein's postulates, and we looked at length contraction and time dilation. And that's really about it. In today's lesson, we're going to go over those two things, but then we're also going to talk about mass dilation and we're going to talk about velocity addition. So how do I actually add up speeds at a higher velocity? When things are going close to the speed of light, how do I add up speeds relativistically? So let's do a little bit of a recap. Einstein's two postulates. The first one is, of course, that the laws of physics must be the same in all inertial reference frames. And his second postulate is that the speed of light in a vacuum has the same value in all inertial reference frames, regardless of the velocity of the observer or the source that's emitting the light. Okay, so these postulates help us, they really helped us to analyze two of these consequences, time dilation and length contraction. So, in time dilation, moving clocks run slow. Time is not absolute. And that was one, this right here, this sentence right here, time is not absolute, is one of the most important sentences that we looked at before, right? And we derived the condition for time dilation. When you go close to the speed of light, time is not moving for you the same as is moving for other people. So we defined these two terms, these relativistic times, right? And that's measured always, it's measured in a frame of reference where the beginning and the end of an experiment occur at two different points. And we also measured proper time, and that's measured in a frame of reference where the beginning and end of an experiment occur at the same point in space. Now, many of my students, many of you who are watching this, would have really mastered this at the end of the unit. And you might be saying, yeah, I actually didn't. But, the hope is that the difference between these two things, proper time and relativistic time, will now be like, oh yeah, okay, now I kind of understand that, because we're going to do an example in a few minutes and we're going to try and get you a little bit back into this type of idea. Length contraction, we had relativistic length and proper length, and it was a little bit more straightforward. The length of something that's measured in a frame of reference where the observed object is moving is relativistic length. So if I see our spaceship fly by, I would be measuring, because it's moving, I'm measuring its relativistic length. Proper length, which we also call rest length, is measured in a frame of reference where the object is observed at rest. Right? So I can measure the proper length of a spaceship, and that would be when it's at rest. I can measure it. And then as soon as that rocket ship starts moving and it's going close to the speed of light, then it would have a relativistic length. All right, here's an example. Let's say I wanted to travel from Earth to Pluto in 1 hour by my watch. What speed would you need to travel? The Earth-Pluto distance is 5.75 times 10 to the 12th meters. So if I want to travel from Earth to Pluto in 1 hour by my watch, I'm on the ship, I'm moving from Earth to Pluto, what speed would I need to travel? All right. Well, because I'm measuring on my watch, I'm the one that's moving, I'm measuring proper time. Okay. I'm in a spaceship. Yes, I'm moving close to the speed of light, but it's on my watch. I don't think time is changing. Time is staying constant. 1 hour, 3,600 seconds. However, I know that I'm on a spaceship. And so what distance am I measuring? Well, the Earth-Pluto distance, which is measured at rest, is 5.75 times 10 to the 12th. So I get 5.75 times 10 to the 12th, and that would be the rest length, right? So when everything is given, this right here is a rest length. So I have these two values. I don't know what the relativistic length is, and I need to know that. But I do know that whatever distance I measure, I'm traveling at some speed v. And I'm taking this much time, because this is what my watch is measuring. I'm taking 3,600 seconds. I'm going to measure some relativistic length, right? Because this distance right here, well, for me, because I'm moving, it isn't going to be this distance. It's going to be some relativistic distance, which is expressed as L. And so I say, oh, well, I've also got an expression for relativistic length, which is here and is given as such. So if I take this equation down here, and I take this equation up here, and I equate these two, because I can, because they are solving for the same thing, I get this very, very, I wouldn't say it's too complicated, but it's a little bit complicated, expression where I can now sub some values in here, T naught and V naught, and I can say, oh yeah, I've got a common factor, and I can simply measure this, and I get, 2.95 times 10 to the 8th meters per second. Now, the algebra in here isn't really that tricky. I squared both sides. I brought this L naught down right here. I squared both sides because I want to get rid of this square root sign. I expanded this. I expanded this. And I collected like terms, v squared and a v squared. And I brought this over to the other side. And I express v squared all by itself. So really the math isn't that hard. I get 0.98 times the speed of light. So that's how fast I would have to travel if I wanted to make it to Pluto in an hour. 0.98 c. Here, we're going to talk about something a little bit different. Okay, we're going to talk about mass dilation. And for the most part, the next couple of slides are all about the derivation of this. But the derivation is actually an interesting one because it uses some uniform circular motion ideas. And we know that uniform circular motion is a really big part of our course in grade 12, and we know that we're going to see it on the exam. So it's nice to review it in a different context as well. So combining circular motion and the Coulomb force, right, with the notion of length contraction, we can easily arrive at an expression for mass dilation. So this is really nice because this is the dovetailing of a couple of different notions in this course: uniform circular motion, the Coulomb force, and length contraction. We're going to come to a very nice expression for mass dilation. Okay, so here's what we're going to do. An electron's moving in circular motion around a proton. The Coulomb force of attraction obviously provides the centripetal force. So here's what we have. Here's the Coulomb force. K times Q1 times Q2, which, because it's a proton and an electron, it's just E, all divided by that distance, the distance between the two of those particles. This is familiar. Centripetal force, of course. mv squared over r. This would be the mass of the electron moving in a circle. So isolate the term for mass. Oh, excuse me, here. If these two forces are, of course, equal, and I get this expression. I'm going to isolate for mass. I'm going to leave mass by itself on one side. Okay, so I get K times E squared over V squared R. But when I have an electron moving really, really fast, the radius of this orbit is contracted, right? Because as soon as V gets really, really big, length contracts. And so if the circumference contracts, then that means the radius contracts as well. So I've got this little expression, r is equal to r naught times 1 minus v squared over c squared. So when things are moving really fast, this is the expression that I've got. M is equal to k e squared over v squared r naught. And watch what I'm going to do. This term right here that I'm moving the mouse around, the ke squared over v squared times r naught, that right there, it looks so similar to this, right? Ke squared over v squared r, ke squared over v squared r naught. This term right here, I'm going to replace. I'm going to call that rest mass. And there it is. Because really, this is the mass that it would have using when it's at rest, right? And so here I get m is equal to m naught over 1 minus v squared over c squared. And this should look very familiar. Okay. Find the dilated mass of a cosmic pion of rest 2.5 times 10 to the minus 28 kilograms if it's moving at a speed of 0.99 c. Here's what we have. Here's what we're going to use. I know the rest mass it's given. I make the substitutions in the equation. Now again, be very careful when you're doing this because this is a spot down here. This denominator is a spot where a lot of people can make silly mistakes, so make sure that you don't make silly mistakes. Take your time when you're going through. And I get 1.77 times 10 to the minus 27 kilograms. So this mass, it was moving at 0.99 c, and the mass actually dilates, so the mass gets bigger. The mass is increased from the rest mass. This is, just for interest sake, this is about 7 times the rest mass. Let's go much quicker. Here's example 3. An electron travels at 0.69 c in a circle perpendicular to a uniform magnetic field of strength 2.0 Tesla. Find the radius of the circle. Hint, go back and look at what we just did. And compare it to the radius without considering mass dilation. So you're going to do 2 calculations. Okay, this is a try this question. I've left you with this to try on your own. One of these cases, I want you to just do it the way that we've always done it. Then I want you to calculate it considering mass dilation. And what you're going to find, here's the answers. If you consider mass dilation, you get 8.1 times 10 to the negative 4 meters. That's the radius of that circular orbit. If you don't consider mass dilation, you get 5.9 times 10 to the minus 4 meters. Right? And so this is a substantial difference. We can look at the solution for this in class tomorrow if you're interested. All right, so next part of this lesson, velocity addition when we've got high speeds. So here's a little example. We've got an atom sitting in the middle. I get an electron that shoots out one way at 0.6. That's this guy here. And then I get another electron over here that shoots out this way at 0.6. I say, okay, I need to find the relative velocity of these electrons. Well, first of all, if this was regular relativity, I'd just add those two. And I'd say, oh, this one's moving away from this one at a speed of 1.2 c. But I know, and you know, that I can't say 0.6 c plus 0.6 c is 1.2 c. I can't do it. If I was going to do this using our relativity symbols, I'd have the left with respect to the right is equal to the left with respect to the atom plus the atom with respect to the right, right? I know that I can always switch an indice around like this by putting a negative sign in there. And so I'd say 0.6 c minus negative 0.6 c, which is equal to 1.2 c. So they're actually moving away from each other with this speed, with this really, really fast speed, right? So it appears as though they're moving faster than the speed of light. But we know that this is a violation, right? So we violated Einstein's second postulate. So how do we add those two speeds together? What do we say if we say, oh, how fast is one moving with respect to the other? We can do it, but we need a new way to add these velocities. And here it is down here. What we're going to say is that the velocity of A with respect to C is equal to the velocity of A with respect to B plus the velocity of B with respect to C. This is exactly the same as what we had before, but now we have to add this correcting term down here. 1 plus the two velocities multiplied divided by c squared. You'll notice when these velocities are nowhere near c, when they're nowhere near c, this becomes some small number over a huge number, and you get 1 plus 0, and the denominator is just 1. Right? So you get exactly the same thing as you had before when we're not talking about anything that's close to the speed of light. But we are talking about stuff that's close to the speed of light, and so this becomes very, very important. So let's do an example. This is our final example of the lesson. Two galaxies are seen receding from the Earth due to their redshift. Galaxy A is farther, and it moves with a speed of 0.8 c. Galaxy B is perfectly in line, but it moves at a slower speed of 0.41 c. So they're both going away from the Earth, but we see them. How fast is Galaxy A moving with respect to Galaxy B? So here's a little diagram. Here we are on Earth. Here's Galaxy B, and it's moving with 0.41. Here's Galaxy A, and it's moving with 0.8. These are not spiders, they're galaxies, okay? So this is what we know. Oh, they could be spiders, but they're not. They're spiral galaxies. Okay, so I have A with respect to the Earth. The velocity of A with respect to the Earth is 0.8 c. I know B with respect to the Earth, and that's 0.41 c. What is the velocity of A with respect to B? So what we're going to do is we're going to use our velocity addition equation, and here it is. And the one thing that we'll notice right away is we've got, do we have this? Yes, we do. We have it right here. Do we have this? And we look down here and we go, well, we kind of have it. We have B with respect to E. What we need is E with respect to B. So we can switch these indices if we introduce a negative sign right here. Okay, so you'll see what we do. We say 0.8 c. Okay, I've got it. Plus, and I introduce this negative sign because that allows me to switch the indices, and I can use this value in here. I have to maintain that switch down here. I get 0.8 c times negative 0.41 c gives me the c squared over the c squared. And I get 0.39 c divided by 0.672, and I get 0.58 c. So these things are actually moving with respect to each other at 0.58 c. So this one's moving away quite quickly. But you'll notice that we can't just say 0.8 c minus 0.41 c and expect to get a correct answer. We don't, because they're moving close to the speed of light.